So it's great pleasure to come here and to give this presentation to show what happened in China. And I was invited by Mad, and I think it's good time to show this kind of things. So then maybe let's start our presentation. Please go to the PPT. Okay, so I will talk about the Chinese quantum computing findings. In fact, it's difficult to divide the quantum computing from the quantum information and the quantum metrology. So I just will talk the whole quantum technicals in China, and I will point out how much of the quantum computing occupied. I'm Xiaobo and come from the CAS Center for Excellent Quantum Information and Quantum Physics. And this kind of center, in fact, is already organized a lot of things and already achieved very impressive things like in the quantum communication, quantum computing, and quantum metrology. And we also belong to the University of Science and Technology of China. Okay, so if you have any question, I list my email. We can talk. Oh, please go to next. Okay, first of all, I will give an overview of Chinese government quantum information programs. So next. Okay, so in China, we have a so-called 5 years plan. This kind of plan, this is from the central government. We see that from 2006 to 2010, that's the 11 5-year plan. About 1 billion Chinese yuan was invested to the quantum technology. And the 12 5-year plan, that means from 2011 to 2016, about 5 billion Chinese yuan go to this direction. And in the 13 5-year plan, since it's just a start from last year, already 2 billion Chinese yuan. Oh, oops, something wrong.
It's okay, you're okay.
Okay. About 2 million Chinese yuan, 2 billion Chinese yuan invested to the quantum technicals. Besides that, we have some budget from the province because the bio I've talked is from the central government. We will also have some budget from the province. So it's about 4 billion Chinese yuan from Anhui, Shanghai, and Shandong, etc., and so on province. And this kind of budget are focused on 3 aspects, including the quantum communication, quantum computation and simulation, and the quantum metrology. So please go to next page. Okay, the organized is in China is typically like this. For the central government, it's usually delivered to 2 big programs. One we call a National Basic Research Program. Another one we call a National Natural Science Foundation of China. This program, 2 programs, has a big difference. The first one, the National Basic Research Program, is mainly focus some field which is close to application. So each project are a little bit larger. It typically has tens of millions Chinese yuan per project. Every year it will support maybe 10 or 20 projects. But for the National Natural Science Foundation of China, is more emphasized the basic research, basic science. So the money is a little bit less. It's about several million or 1 million Chinese yuan, but it will support a lot of directions in the quantum technicals. In the quantum, every year maybe several hundreds of projects we are supporting from this program. Okay. Besides that, most of the money is just directly come from the Chinese Academy of Science and the Ministry of Education, since almost all the university and the institute belong to these 2 departments. So that means besides the program budget, we also can obtain some budget from CAS and the Ministry of Education. And as I've mentioned before, also there's some budget from the province. So we just count how much of the budget go to the quantum computer. It's a rough number. It's about 1/4 1/4 of the total budget go to the quantum computer because quantum communication I will show later. Indeed, in China, developed very good. So most of the money go to there because go to some big project. So it's about 3 billion Chinese yuan already go into the quantum computer regimes. Okay, please go to next. So. Although that we still believe this is not so high efficiency to really improve to push the quantum techniques go further, go quickly. So nowadays we are trying to establish a future national project. So please go to next. Okay, this kind of national project is first of all the CAS Center is our center is. Now playing a leading role in this organization. And it will have 2 parts. One part is we will have a national science and technology project on quantum information in the next 15 years, similar to the Europe Quantum Technology flagship. And based on this budget, we will establish a national laboratory as well. This is just for quantum information science. Okay, again, this kind of project and this kind of laboratory will also focus on the quantum technical, including the global quantum communication network, scalable quantum computation and quantum simulation, and the super resolution quantum metrology. Okay, please go to next. Okay, before I really introduce this kind of national laboratory, let me introduce a little about the CAS Center. In fact, this center is already become, the center of the quantum technical in China. It is jointly supported by CAS and the Ministry of Education. And annual budget now is about 100 million Chinese yuan per year, and is hosted by USTC. And it includes top institute and university on quantum physics. For the institute side, you can see Shanghai Institute of Technical Physics, Institute of Semiconductors, Institute of Optics and Electronics, and the Nanjing University, and several excellent groups among China University, like Tsinghua University, Peking University, Fudan University, and so on. Quite a few university groups join us. Okay, please go to next. Okay, for this center, in the last 10 years, I think the biggest achievement is coming from the quantum communications. We have 2 aspects. One is the National Quantum Communication Backbone Project. It is inner city quantum communication backbone with 32 trust relays. It's the total length is about 2,000 kilometers, and it already applied to financial and public affairs and a lot of places. Okay, and it is the test bed for quantum foundations, and it's already open at the end of last year. It's running now. And please go to next. Okay, another I think impressive things for this center is we have launched a quantum science satellite, MODS, and it's already landed last year. And here, this is a picture we tracking the satellite from Xinlong near Beijing. And please go to next. And next. Yeah. So we have 3 science missions. The first one is to realize a high-rate quantum key distribution, QKD, between the satellite and the ground. And next. And the other 2 is quantum entanglement distribution from satellite, test of spunky action at a distance under strict Einstein locality conditions, and quantum teleportations between the ground and the satellite. In fact, this kind of 3 missions already succeed and already published on Nature and Science. So if you're interested for that, you can check it. Okay, please go to next page. Okay, let's back to the National Laboratory for the Quantum Information and Science. So we would like to organize this kind of a national laboratory like this. The headquarters is located at Hefei, and it will focus on the quantum information processing with photon, solid state, and molecular systems. And it will integration of quantum communication system and quantum metrology. And in Beijing, it's one of the branch. This kind of national laboratory, only one headquarter and two branch. And Beijing is one of the branch. And we are focused on the quantum materials, quantum computation with trapped ion, and topological quantum computations. And in Shanghai branch, we will focus on the quantum computation and simulation with ultra cold atoms and superconductors and photonics. So I was just, I was working in Shanghai branch, the CAS Center. So we will go further in the superconducting quantum computer in this place. And we are in Shanghai. We have also developed satellite-based free space quantum communications and the application of quantum communications. Okay, please go to next. So the target of this this national laboratory, also there's three aspects. One is quantum communication, and another one is quantum computation, and there's also quantum metrology. So for the quantum communication, it's towards the global quantum communication network. It will establish the widespread fiber quantum communication infrastructure. It will be compatible with the classical and optical communication networks. And you see there's a lot of fiber, like from Beijing to Shanghai, the first one. And the quantum repeater, we would like to improve the repeater efficiency. It can enabling a quantum communication at a range of 1,000 kilometers. And we would like to establish the technical standard for quantum communications. Go to next. Okay, and also for the quantum communication, we would like to set up a quantum constellation covering the whole Earth directly with the MEO and the GEO satellite, which will be launched in the next 5 to 10 years. And the global quantum communication infrastructure, we give it a name like quantum internet. Okay, please go to next. For the quantum computation and the simulation, in fact, this kind of national laboratory will support most of the way to realize the quantum computing, including here at least part of them not so complete, superconductor photons, cold atoms, topological trap ion, NV center, NMR, quantum dot, and the whole budget, 1/3 of the whole budget will go to quantum computing. But for the whole budget, we still, it takes time. This kind of project, in fact, start from 3 years ago. We start to apply this to the central government, maybe 2000, maybe 4 years already, 2013. But still, because it's too big project, it's still it takes time to really write the budget. But at least it's on the order of it's bigger than the central government have delivered, like in the 5 years plan. It's much bigger than that one. So it's our hope, and we are close to succeed. Maybe it will start from last year, but this year is impossible. At first, we believe maybe this year it will start. Maybe we'll go to next year. Okay. So the target of the quantum computing is just go to the scalable quantum computations. I think here what we mentioned is not so, it's somehow preservative. Like you see, in the next 5 years, quantum computer with 50 to 60 qubit, beating the classical supercomputer in specific tasks. So I think maybe in US, maybe we'll realize maybe within 2 or 3 years, I don't know. In the next 10 to 15 years, quantum computer with hundreds of qubits, mimicking condensed matter physics and some interesting problems. Oh, sorry, should go to next page. I'm sorry. Okay, so this is our target in the quantum computer and quantum computation and quantum simulations. So I think for the superconducting quantum computing, it's highly possible to just realize these two tasks. Maybe I heard from Martinez, maybe it's more, maybe we should go further. We also feel so. I think there's big chance to go further. This is maybe the safe, at least we should go to this kind of things. Okay, please go to next page. So for the quantum metrology, we just want to use fiber frequency transfer. It has much better instability. It will go to 10 to minus 19 and 4 magnitude better than the microwave schemes. So this is one of our way to use quantum metrology to change the situations. Okay, please go to next. And we want to have a high precision ground-based server time server system. It's just around here we see we would like to organize the network in China, and to build the world's largest optical fiber time frequency transfer network, and the most advanced indicator of the performance. It has 3 primary station, 5 secondary station, and then 19 territory test stations. Okay, please go to next. And also, we want to use a very precision optical clocks and large-scale optical time frequency transfer network to realize high precision navigate and timing. So it's already done some work in China now. So this is also the task belong to the quantum metrology. Okay, let's go to next. Okay, let's talk a little bit about the commercial partners in China in the quantum technicals. Okay, go to next. So in fact, in China, at least here, quite a few famous names. They are currently most interested in our quantum computation technicals. In fact, most of them are our customers. We have established a company to run the quantum communication network from Beijing to Shanghai and run something from the satellite. But they are really help us to test it, and they are customers. They're using our quantum communication network to encrypt their data. So here, what we list is most collaborated with CAS Center is just for the user for the quantum communications. I think quantum communication nowadays is more attractive if you consider the commercial way. So because it's already you can use it, you can just encrypt your data with very good key. So that's important. And only one, Alibaba, sponsored us. He is not really going into the hardware of the quantum computer. It's just sponsored us since last year. And we established the CAS Alibaba Quantum Computing Laboratories. So for me, they give us some budget, some financial support. So that's why, in fact, in CAS Center, I just moved from IOP China, from Beijing to CAS Center Shanghai last year, at the beginning of last year. After about 2 years, we can establish our lab very quickly. In fact, it's just very helpful from the money come from Alibaba. So that's important. Please go to next. So in the last few minutes, I will show the progress on superconducting and photonics quantum computing. Okay, go to next. Okay, in fact, in China, not very much group really did the research on the superconducting quantum computing. Here I list all of them. Only you see in Beijing, we have 3. IOP China, Tsinghua University, and Beijing Computational Science and Research Center. Oh, I should mention this is only for experiment. For theory, that's quite a lot of group. Okay, so I was working in IOP China since 2013, and then I moved from IOP China at the beginning of 2016 to the USTC Shanghai, which is the CAS Center. And I also collaborated with Zhejiang University, Hao Hua Wang. He is a postdoc work in John Martinez group. So that means these 3 groups, IOP China and USTC Shanghai and Zhejiang, I will mainly talk the effort from these 3 groups. And another universities, Nanjing University, are doing some research on superconducting quantum computers. So I think compared to the scale, so in US is quite small, but we are really want to push this kind of things forward and become good and good, better and better. Okay, please go to next. Okay, in fact, for me, at first I was focused on the flux qubit, but at that time, the flux qubit, the T1 time and T2 time is not good enough. And XMO, we see XMO and the transmo system indeed has very much better coherence time and properties. So we just start I just changed to direction a little bit to the XMO qubit system. We start from several qubits, and now we can have a good 10-bit system. We can really test it, and we are designing and fabricating a 20-qubit system. It's okay for 10-qubit system. It's already complicated enough, and yeah, for the 20-qubit, we meet a lot of problems. And I fully agree with in the morning, John Martinez, Professor John Martinez was talking about just the quality is much more important for the quantities, for the numbers of the qubit, because we are using a semiconductor-like processing, fabricated processing. You can easily to prepare a lot of qubit on one chip, but the difficult thing is how to improve the qualities of the qubit. Especially you integrate a lot of qubit in one chip, and it's very, very difficult to have a high precision gate, especially the 2-bit gate. Nevertheless, we make a big effort on this direction. It's become better and better. We are not saying we are good enough, but it become better and better. E.g., I list some part of the parameters here. For our XMO qubit, the best T1 is about 30 microseconds, 10 to 20 on average. And the T2 star is above 20 microseconds and 10 to 10 on average. And for our single bit gate fidelity is above 99.9. That's the randomized benchmarking measurement. And for 2-qubit, the best result is 99.1. Okay, please go to next slide. Okay, in order to improve the readout efficiency, we also fabricate our JPA preamplifier. It's indeed help. You can see we can separate the readout state, 0, 1 state very much, and indeed improve our readout contrast. We just follow the JPA type from this paper, at least here. So now it's good for 6 qubits. The bandwidth is not very high, but okay, it works and it really help our readout. Okay, please go to next. So this is our single bit gate RB measurement. We test quite a few qubits in one chip and different type of single bit gate. We will see normally it's higher than 99.9 because when you really do this kind of single bit gate, it's not the most complicated part because you can separate the qubit and you can really good. But for the, please go to the next. So for the CD gate, for the 2-bit gate, that's indeed very, very difficult. We spent a lot of time to optimize it. And we can, this is in a 9-qubit version samples. We can achieve the 99.1 fidelity. And most of the gate can be above 98, and this is our best result. We still believe there's a lot of things we need to optimize and to really go to scale up. So I think if we really seriously consider the large-scale quantum computer, this kind of issues should be carefully solved, and seriously we should solve this kind of problem in advance. Otherwise, it's very, very difficult to talk about many qubit system and how they running. And I know algorithm guys seems very happy to see we can have a lot of qubit and run the algorithm, very lot of steps. But indeed, I think in our qubit system, at least in our qubit system, it's the noise will kill a lot of things if we cannot improve the 2-bit gate fidelities. Okay, please go to next. So this is our 10-bit versions. We just have complete connections. Please go to next. So we design a central frequency, central resonator. It's connected to all the qubits. It's not really a scale up because the resonator, the space of resonator is limited, but you can go to 10. We are trying to 20, but at least you will see in this experiment, it indeed help. It will, because all the qubits can couple together via this kind of central resonators. Okay, please go to next. So here is the list of the parameters. We will see that, please look at 9, 2. You will see the T2, T1. T1 of our system is just as I said, is on the order of 10 to 20. Someone is close to 30. And for the T2 star, because we are not working at the optimal point, it's a little bit short. If you go to the optimal point, it goes to 20, 10 or to 20. Okay, so the top frequency is not so precisely shooted. But nevertheless, our designs, we can tune the gap a little bit, not a little bit, we can tune the gap. So in fact, not a big issue. If we really want to, you really go to the design, there's no tunability, I think we should improve this kind of fabrication precision more. Okay, please go to next. So you see, because we have full connection of this 10 qubit, indeed we can do some amazing things. Here we just show we can entangle all the 10 qubit, and this kind of GHZ state has a fidelity higher than 66%. It appears in PIL papers. If you are interested, you can look at it. Go to next. Okay, we also demonstrate the algorithm, HH algorithm on a 4-bit systems. And anyway, you can see in this paper, it's very, very simple version of HH algorithm. It's just 2x2 linear equations. If without the error correction, this kind of things can only demonstrate something. It's not really, practical, not really practical. Okay, please go to next. So we will see for this kind of algorithm, for all the input state, we have about 85 or 89 fidelities. Also, this work appear in PL, please. Okay, next. And I will spend another 2 minutes to just show our effort in the photonics quantum computing. In fact, this kind of direction in CAS Center, they have a very, very good achievement. It's always the record of 3 photon entanglement GHZ and 4 photon, 5 photon, and 6 photon, 8 photon, 10 photon. Indeed, we have very good technical in the photonics operating generation and collection of the single photon. So that's good. And we also, Xiao Lu and under Jim Pine, you also write a review paper and to review such kind of things. Go to next. So also in the photonic systems, they have already demonstrated almost all the important. It's just a demonstration. Say it again. It just demonstrated all of the algorithms we know. So it's published a lot of results. Okay. So overall, I think if our national laboratory start up, we can accumulate and focus more people and resource together to just go to the research and the quantum computing and the quantum communication and the quantum metrology. We hope this kind of things can happen soon. So at last, thank you for your attention. Please go.
Okay, so I think technically we can work questions, correct? As long as someone speaks into a microphone. Great. I got a thumbs up. So if you have a question, please raise your hand.
I think I saw you said about 1/3 of your budget is going to quantum computation and simulation.
Yes.
You have 2 other segments. You have metrology and you have communications. What's the split for those other 2 segments?
I think maybe quantum metrology is only about 1/5. And most of them still go to the quantum communications because it's more practical, I think. I didn't have precise numbers, but it should be on the order of that.
Okay, so Xiaobo, we really, really appreciate you again being as flexible as you have been, and we will be connecting with you live here, hopefully very, very soon. But I'd like everyone just to give Xiaobo again a really great round of applause. It was a super presentation. Thank you very much.